Hello, everyone. Thank you, everyone, for showing up to the RAL seminar this week. Appreciate the attendance in the building and also for those that are online. Today we have Alyssa Stansfield. She's an assistant professor in the Department of Atmospheric Sciences at the University of Utah. Her research combines high-resolution atmospheric models with observations to study the relationships between high-impact extreme weather events and climate, with the hope that this information can be used to better prepare society for the weather events of the future. At Utah, she has taught climate dynamics, introduction to atmospheric science, and the introduction to Earth system science, and was awarded the department's Excellence in Teaching Award this past spring. She had her bachelor's in meteorology from Rutgers University and her PhD in marine and atmospheric sciences from Stony Brook University, and completed a postdoc at Colorado State University before moving to Utah. Where we met was she's a co-PI on the seeded and natural orographic winter storms and catchment processes evaluation, which is SNOWSCAPE, that everyone uses and everyone forgets all the words that go into the field campaign that happened this past winter in Utah. She helped to organize students to support the Radiazon launches near Ogden, Utah, and helped also launch some balloons herself. Just briefly, there'll probably be a seminar later in the year on SNOWSCAPE, but it was an NCAR-led multi-organization field campaign in northern Wasatch Mountains to collect observations to support an evaluation and optimization of Utah's weather modification program. And with that, please join me in welcoming Alyssa.
Great, thank you, Nick, and thanks for inviting me and everyone for coming. I'm really excited to be back at NCAR. I've been here in a little bit. So today I'm going to be talking about kind of a variety of topics that myself and my research group have been working on over the past year, and I'll have some very preliminary data from SNOWSCAPE at the end because it just ended in March, so we're still QCing the data and such, but I wanted to talk about it a little bit and what I plan to, and my student plans to do with the data. But kind of broadly to try to tie everything together, I tend to investigate precipitation processes specifically over the continental US, and a tool that I often use is objective storm tracking. And so my research group at the University of Utah, I kind of think as myself and my group is kind of this bridge between people who think about large-scale climate dynamics a lot, and people who are a little more on the weather, small-scale weather side. I've kind of been trained in both. I have my BS in meteorology, but kind of did a little bit more climate research in my PhD. So I've kind of been switching back and forth. But I think fundamentally my research question that I try to answer through all my work is what are the fundamental relationships between weather extremes and climate? And so I really got interested in doing research because I grew up in New Jersey and Hurricane Sandy hit New Jersey in 2012, which was my senior year of high school. And so seeing the damage that this hurricane can do, and it's pretty rare for a hurricane to hit New Jersey and do that much damage, kind of got me interested in doing research and studying meteorology. And specifically, we know that most of the deaths from hurricane landfalls in the US and globally are attributed to water hazards. So a lot of it comes from storm surge like Hurricane Sandy, but there's also a good amount of the hazard comes from rainfall. I think Hurricane Helene is probably the most recent unfortunate example of this, where Asheville, North Carolina, and the surrounding areas received over 1,000-year rainfall or something over the 3 days. It was a really rare, devastating event. And so this kind of motivates my research in hurricanes, rainfall, and other storms to see extreme precipitation becoming more frequent over time. And so I'll just highlight a paper I was involved in that just came out like a month ago from Dmitry Kalashnikov, I probably pronounced that wrong, at UC Merced. And he looked at the impact of tropical cyclones on very extreme rainfall events. So basically the top 2 rainfall events every year at weather stations across the country. So these points that are colored in are points that have seen top 2 extreme rainfall from tropical cyclones over the past pretty long, I think 80 years of data or something like that, maybe a little shorter. And so what he did then was extend this a little bit and connect tropical cyclones to atmospheric rivers. So kind of connect 2 data sets together and try to see kind of the extended impact of tropical cyclones on rainfall, where sometimes they'll transition, the weaken, not technically be a hurricane or a tropical cyclone anymore, but they're still impacting water vapor transport. And when you do that, you see that tropical cyclones impact a lot larger area of the United States than you typically would think of as just the Northeast and the Southeast and the Texas area. And we also found in this work an upward trend in the number of tropical cyclones causing extreme precip in the Northeast and Southeast CONUS since 1980. Those were the 2 regions with the significant upward trend. But I think this kind of demonstrates that maybe we are starting to see these signals in extreme precipitation amount increasing over time. And so a lot of my previous work has focused on tropical cyclones and trying to understand the physical mechanisms that are causing tropical cyclone precipitation increases. So again, I've done kind of this research across scales in my PhD work with my advisor at Stony Brook. I got to do these idealized CAM simulations where we had tropical cyclones like all over the world, because it was a basically tropical environment everywhere, and look at how the rainfall and the tropical cyclones changed as you increase the sea surface temperatures. And then in my postdoc at Colorado State, I did some more, again, idealized modeling of tropical cyclones, but this time convection permitting kind of tropical cyclones in a box simulations, increases sea surface temperature, and was looking at how precipitation kind of across the storm in the inner core outer rain bands, and also the convective structures changed with increasing sea surface temperature. And I'll talk about that work a little bit later. But most recently, kind of my plan for my postdoc was extending that idealized WRF modeling to more realistic simulations. And CONUS404 was kind of right there as a really convenient data set to use to look at some long-term convection permitting simulations that have tropical cyclones in them. So I won't go over CONUS404 too much because I'm sure a lot of people here know more about the simulations than I do, but there are 4-kilometer grid spacing over the entire CONUS from 1980 to 2022. They have initial and boundary forcing from ERA 5. And so in my work, I named it WRF historical, so over the historical period. And then they also have what are called pseudo-global warming simulations, where you kind of add a climate change signal to the ERA 5 forcing and can kind of look at the weather events that happened in the simulations, what they would have looked like under, say, a warmer, wetter environment. And so the CONUS404 PGW simulations are based on, or the forcings are calculated using the SSP 37 radiative forcing scenario from the IPCC. And so it's important to remember with PGW simulations, they kind of have to answer a very specific question. They're not going to help us answer how the frequency of tropical cyclones, genesis, or landfalls may change, but you kind of can look at the events that happened and see how maybe their intensity or rainfall or other properties may be different under a warmer world. And so these I refer to as WRF future. And so again, I have done a lot of kind of subjective storm tracking. So I use the software called Tempest Extremes a lot, which does tracking of more than just tropical cyclones. But I kind of, for this work, I kind of helped the objective tracking cheat a little bit. I filtered the CONUS404 sea level pressure fields to exclude points outside 3 degrees of the center of observed tropical cyclones from the IB tracks observed data set. This is just to help the tracking algorithm work as well as it could, basically. And so then I matched all of the tropical cyclones that were tracked in WRF historical to observed storm tracks. So this is just an example of the observed tropical cyclones from the year 2017. and then the tracks from the WRF historical simulations in 2017. And so those green tracks on the left are the ones that match the storms in the model, and the red ones are ones that did not have a match. So most of the ones that didn't match are because they stayed too close to the model domain boundary, didn't really form, or just stayed too weak. So, but most of the storms that were strong and made landfall in the US, we have matches for. And all in all, of the 218 storms tracked in the WRF historical and the model, we have observed tropical cyclones. So they weren't just making up tropical cyclones that didn't happen, which is good. And so what we can then do is track these storms and look at their intensities and other properties as they evolve. And we kind of have these matching pairs of storms in the WRF historical, which is on the left, and the WRF future, which is on the right. And so tempest extremes is really nice because it can also kind of follow the storm and extract variables around it. So for example, for a given storm, I can take out within like 500 kilometers around the storm center, accumulated precipitation or ice and snow, or really whatever model variables you want. And so just to begin to look at this, so here are comparison of tropical cyclone intensity between the WRF historical, which is the kind of background blue distributions, and the observations, which is the green. And so the left is maximum wind speed and the right is minimum sea level pressure. So kind of two measures of storm intensity. And the model, again, does pretty well. You can't expect the model to exactly match the observations for various reasons, but overall the mean intensities are very similar. There's just some underestimation of like the most intense storms, which I think is to be expected, especially because the tropical cyclones in ERA 5 they don't reach the highest intensities anyway. So I think the model kind of inherits some of the biases from the boundary forcings. And so next I looked at trying to compare their precipitation. So I did my best. So I'm comparing it to the NASA iMerge product. And I converted that from half hourly to hourly to match the temporal resolution of CONUS404. And then I regridded the model and observations to the same like 0.1 degree grid. So there was a little more of a fair comparison. So on the x-axis is, so each of these points is an individual time in a tropical cyclone lifetime. The mean precipitation within 5 degrees of the center. So the x-axis is WRF historical, the y-axis is observations, and the dots are colored by the difference in intensity between the observed storm and the model storm. And so this was just to try to figure out if the difference in mean precipitation was like correlated with the difference in intensity. And the correlation is, actually surprisingly not very strong, which may be reasons I'll get to later. And then I looked at a metric of extreme precipitation, so 99th percentile precipitation in each time step of each storm's lifetime. And here the model seems to overestimate the extremes a little bit. And now this time I colored the dots based on the difference in mean precipitation. So to try to see if the biases between mean precipitation are correlated or related to the biases in extreme, which they are definitely more related than the intensity differences. So what's interesting is, so the purple dots are where the model tends to underestimate the observed precipitation. And so when that happens, you see we're closer to that 1-to-1 line. So when the model underestimates the mean, the extremes tend to be more similar. When the mean precipitation in the model and the observations match pretty well, so that's kind of the very light colored dots, the model tends to overestimate the extremes. And then when for the green dots, when the model overestimates the mean precipitation, also overestimates the mean or the extreme precipitation. So just trying to get an idea of how the biases may relate to other properties of the storms. And so next, another thing I like to do is kind of separate the inner core of the storm with the outer rain bands. In this case, I define the inner core as all points within 1.2 degrees from the center. And then anything outside that within 5 degrees was the outer region. And so here's the relationship between the mean precipitation on the y-axis and the storm intensity measured by the minimum sea level pressure for the WRF historical in the blue, observations in the green. And so we see that this is for the inner core only. The inner core precip has a pretty strong relationship with TC intensity. That's to be expected. But interestingly, there seems to be a bit of a stronger relationship between the TC intensity and the mean inner core precip in the WRF historical compared to the observations. The regression line's a little bit flatter. And then looking at the outer region, the relationship between the storm intensity and the outer region mean precipitation is much weaker. That's not a super new result. Other people have found that there's just not as much of a relationship there. And here the model seems to do better at reproducing this kind of weaker relationship. So another collaborative work that Julia Kukulis, who was a postdoc in M-Cubed, I got to collaborate a little bit with her on this really interesting work looking at precipitation efficiency of all types of storms actually in CONUS404. And so she was able to calculate precipitation efficiency using different methodologies and compare it between different storm types. So encourage you to read the paper because it's a really interesting paper, but I'll just focus on the tropical cyclones here, which are in that purple box. And so the observational estimate of precipitation efficiency is the box all the way on the right. And then the left two are estimates from CONUS404 using different methodologies. And so one interesting finding was that the precipitation efficiency in TCs has the least amount of variability compared to other storm types, like by far. And we did some analysis to see if this was just because we're obviously only modeling like part of the TC lifetime in CONUS404 since the placement of the model domain boundary. And that turned out probably not to be the cause. So it maybe is potentially a natural signal that, yeah, their precipitation efficiency maybe is much more consistent than other types of storms. And we also split the precipitation efficiency calculations into the inner core of the TCs and the outer region, it's just on the right. And so we see maybe precipitation efficiency is slightly lower in the outer rain bands, but I don't know, the difference in the variability seems to depend a bit on the calculation method. But yeah, overall, the model does pretty well at replicating the observed results when you use the same methodology. So again, really interesting paper published early this year in JGRA. Okay, getting to the differences when we look into the future. So comparing WRF historical to WRF future, this is just showing the kind of mean percentage increase in the mean values of these different variables on the y-axis for in WRF future compared to WRF historical for tropical cyclones only. So we saw about a 9% increase in mean precipitation, about a 9% increase in column integrated water vapor. And one interesting thing is that the column integrated ice increases way more than the column integrated liquid. So probably due to much stronger updrafts lifting water vapor up above the melting layer. Looking a little bit more into the changes here. So this is kind of similar setup here. So we have the WRF historical mean precip on the x-axis, WRF future on the y, with their intensity, TC intensity difference colored. And so again, not a huge signal in the TC intensity difference. If that was kind of the main driver, I'd expect all of the green dots to be like above that 1-to-1 line, all of the purple dots to be below, but they're a bit more scattered. And when you do these calculations, ultimately more of the dots are above the 1-to-1 line. I forget the exact number or percentage. So generally mean precipitation for TCs tends to increase, but it doesn't happen every time, right? There are some instances, or many instances, where the mean precipitation is higher in the WRF historical. And then here is the figure, the same figure for 99th percentile, again, with the colors, meaning the difference in mean precip. And now we see that those whitish dots, which is where the mean precipitation between WRF historical and WRF future is not very different, pretty close, is at that 1-to-1 line. Now where WRF future mean precip is higher, the extreme's also higher, and then the vice versa, where the WRF historical mean precip is larger, the purple, it's below the 1-to-1 line, so the extremes. So that's more consistent. And I'll say this result of, there's not always a TC precipitation increase in PGW simulations like this for every tropical cyclone is consistent with a paper that came out 2 years ago from Colin Zarzicki, who looked at kind of similar type of PGW simulations run by the DOE, I believe. And so when I was at Colorado State, I got kind of involved in this NASA INCUS mission, which is really launching satellites fairly soon. And it stands for the Investigation of Convective Updrafts. And its goal is to actually be able to measure convective mass flux in the tropics using 3 small sats to get at the question of why do convective storms, heavy precip, and clouds occur exactly when and where they do. And so Kristen Rasmussen, Sue Van de Heever's the lead of it at CSU. I kind of started getting involved in this project and thinking about being able to measure mass flux in tropical cyclones potentially. And so this is the equation for mass flux and how it's calculated. It's essentially just vertical velocity times air density while incorporating the water vapor mixing ratio. And then so I calculate it and basically integrate it throughout the troposphere to get kind of this vertically integrated mass flux quantity. The plot on the right is just an example of what the mass flux at 2 kilometers looks like in my idealized convection permitting WRF simulations. And so I looked at this relationship between this vertically integrated mass flux and tropical cyclone intensity, and when only taking the mean of the mass flux in the inner core of the storm, which is the left, and the outer rain band, which is the right. So again, this is not super surprising because we know the outer rain bands are like decoupled a bit to the intensity of the tropical cyclones. Whereas in the inner core, we see this really strong relationship. And again, these are idealized WRF simulations. So taken with a grain of salt. But it was interesting to see, such a different relationship. And then I did the same thing, but on the y-axis now, instead of TC intensity, is TC mean precipitation. And we see that that very strong linear relationship maintains between mean vertical mass flux and mean precipitation. And then it's a little bit, it's not as strong in the outer rain bands again. And so part of my extension with CONUS404 was I wanted to try to look again at vertical mass flux in tropical cyclones, how it relates to precip, how it may change in the future. So here are similar plots. So this is TC intensity compared to the inner core mean vertically integrated mass flux on the top, and then the outer region mean vertical mass flux on the bottom. And so as expected, there's that pretty strong relationship in the inner core and less strong of a relationship in the outer region, similar to the idealized simulations. And they're just based on this, there isn't a super big increase in mass flux, although the mean does increase, as I'll show in a minute. And then here's the same idea, but now the x-axis is the mean precipitation again, instead of the TC intensity. So I think ultimately it shows similar results to the idealized, but the relationship between the mean precipitation and the and the outer region mean mass flux is much stronger than it was in the idealized. I think, yeah, that's due to maybe the simulations being a little too idealized, maybe what they have going on in the outer rain bands is not as realistic as what you see in the real world. But we do see the inner core mean mass flux increases by about 16% in more future compared to the historical, and then about 8.4 in the outer region. One thing I was thinking about when I was putting this presentation together is that, so the mean inner core mass flux increases by like 16%. The mean inner core precipitation increased by less than that. I think it was 11 or 12%. So I'm starting to think about, again, precipitation efficiency. We have all this mass flux going up. Does this maybe imply that the precipitation efficiency actually decreases since the precipitation doesn't increase as much as the mass flux does? I think they have to think about it more and maybe talk to Julia. I don't know if she was planning to do her analysis on the PGW simulations for precipitation efficiency, but I think it would be interesting to look at. And then this is just looking at this left plot you've seen before. So this is the mean precipitation where the colored dots are the intensity difference. And so then what I did was I colored the dots instead by the mean mass flux difference. And you see that the relationship in the kind of the pattern of the dots is much more clear, where the change in mean precipitation is much better related to the change in the mean mass flux versus the TC intensity measured by the minimum sea level pressure. So I think all this means is that the mean mass flux is just kind of a better measure of that secondary circulation in the tropical cyclone that really drives the precipitation production. So that's all I have for the TCs in CONUS404. So just to reiterate, WRF historical underestimates the mean sea level pressure of the most intense TCs, but overall does pretty well with the intensity of the storms. And there's maybe a bit of an overestimation of extreme precipitation. The precipitation differences compared to observations are not really closely related to the difference in TC intensity. WRF historical does capture the different relationships between TC intensity and inner core precip versus TC intensity and outer region precip. So that shows us that CONUS404 is kind of simulating these different relationships in the different parts of the tropical cyclone well. And then there's increase in most of these kind of thermodynamic variables in more future, especially the atmospheric water content. And an important thing to note for these PGW type simulations is that precipitation is not increasing for all of the storms. There are instances where the precipitation decreases, both mean and extreme. So I just want to shout out Chris Johansson, who was an undergrad working in my group, did a lot of this work and helped me a lot. And then Kristen Rasmussen is collaborating with me on this work. And also thank the Wilkes Center at University of Utah, because they funded a lot of Chris's time working on the project. And so I have a paper in prep that hopefully will be submitted soon about this work. But I think thinking about what else I want to do with TC precipitation stuff, I think hopefully we'll get some observations of mass flux with INCUS, which would be really exciting to see what we can learn about tropical cyclones. Potentially expanding my analysis to global convection permitting simulations where I'm not limited to just storms that are close to the US and making landfall. And I do, as I mentioned, I have this data set of these matched tropical cyclones to observations and matched to the PGW simulations for CONUS404. So if anyone is interested using this data, it's all on Derecho and available. So if anyone's interested in it, you can just contact me to use it. And again, it's easy for me to also create this with other data sets as well using Tempest Extremes. Okay, so I've continued some work on CONUS404 beyond just tropical cyclones. And I'm starting to try to think about this question of how kind of larger storm larger scale storm systems and kind of large scale environments drive extreme precipitation events. So many studies have shown that kind of mesoscale processes that are organized, triggered, or enhanced by these larger scale storm systems and forcings are the things that really create extreme precipitation. And so kind of thinking about this question, we have been, my PhD student and I have been kind of linking MCSs in CONUS, CONUS404 and observations to larger scale weather systems across all seasons, and looking at how CONUS404 represents these connections between MCSs and other storm systems. And so my PhD student built this kind of connected objective tracking framework based on tempest extremes, and also this framework called Cyclones, which is a kind of generalized low pressure system tracker and classifier. And we also tracked fronts. So we were tracking low pressure systems, fronts, and MCSs across all of the US using ERA5 data for the low pressure systems and fronts, and then the NASA merger and iMerge data sets for the MCSs, and doing the same in CONUS404. And so this figure is kind of complicated, but I'm trying to demonstrate kind of what this tracking and classification framework looks like. So I think, yeah, this top row is CONUS404, and then this bottom row is ERA5 and observations. And so this is just showing a snapshot of time on January 1st, 2021. And so these darker blue lines show tracks of low pressure systems. So here, this looks like a extratropical cyclone of some sort, or maybe a subtropical storm moving across the eastern US. And it has this kind of convection or cloud system associated with it, which has been picked up by the MCS tracker. And because it's tagged green, it is kind of considered associated with this extratropical cyclone low. And so one thing I'll point out is that this is definitely not a perfect system. There are differences, and it's hard to make perfect. You can tune these things infinitely. But yeah, there's differences, say, in this system in the Northwest, where this is observations, kind of looks a bit stronger in the brightness temperature, whereas it's a bit muted in CONUS404. And so CONUS404, the tracker doesn't even pick it up. And then it is tagged and tracked and classified in observations. And so I'll note one thing that one challenge we've tried to overcome is that it's really, really hard to do this objective tracking across the whole US because of the complex topography in the Western US. A lot of objective tracking literature actually tends to just ignore complex topography. They just say if anything's up more than a couple hundred meters above sea level, we'll just not deal with it. So we didn't want to do that because we wanted to focus on the whole US and be able to track these systems, as they evolve over the US. So we kind of had to come up with some strategies to be able to track over complex topography. The kind of key to it, or that we figured out, was using the terrain following coordinates in the model and reanalysis instead of using pressure level. And it seems to work pretty well, but that was difficult. And another kind of highlight is that we completely objectively define the sizes of the LPSs, because those are really important to kind of relate MCSs to. And so in the past, sometimes you'll choose, like I did before, just a 5-degree radius around a tropical cyclone, or a bit larger one around an extratropical cyclone. But we kind of created this objective measure of the size of the influence of the low pressure systems based on vorticity. Yeah, so obviously there's a lot of intricacies of this tracker. I don't have time to go over all the details and even all the results, because my PhD student has done a lot of work on this, but I'd be happy to discuss it with anyone afterwards. Okay, so this is showing the climatology of low pressure systems. So larger scale synoptic scale systems over CONUS in CONUS404 and then ERA5. So unsurprisingly, they look good, right? Your CONUS404 is forced by ERA5. So if these looked really different, I'd be concerned. But they look really good. Basically, the different colors are just different kind of categories of low pressure systems. So we have tropical are the red ones, extratropical are the green, which includes subtropical storms. There's like a dry branch that's maybe more thermal lows or systems that just don't have a lot of moisture. And then high altitude, which is basically low pressure systems over very high altitude places in the mountains, which only really occur in CONUS404 because the topography is higher. But overall, yeah, the seasonal cycle and kind of the counts match really well. So that's a good sign. And so next, again, there's a lot in these figures. This is comparing the MCS climatology. So again, we kind of track the MCSs separately, and then we're able to associate them with the LPSs and fronts based on these objective kind of measures of each of their sizes. And so again, CONUS404 is on the top here, and then the kind of combination between ERA5 and observations is on the bottom right. And so again, broadly, pretty good. There's definitely a really good match between the tropical kind of branch of the systems, the cycle and the extratropical, and even the dry is really, the seasonal cycles captured. The spatial occurrences are also really good. I'm not going to show that here because it's just a lot, but for both the LPSs and the MCSs, comparing the spatial occurrences between CONUS404 and observations is really good. The big difference here is just the kind of raw counts. So you'll notice kind of the size of the bars in ERA5 and observations in CONUS404, especially in the winter, are very different. And so we tracked this down to the way that we were converting outgoing long wave radiation to brightness temperature, because the observations we have are brightness temperature, CONUS404, and models tend to spit out outgoing long wave radiation. So we just used kind of this simple equation that's been used in the literature before to convert OLR to brightness temperature in CONUS404. And this just tends to have like a warm bias in the brightness temperatures. So just not as many like MCS are being detected. Again, it's like a loose definition of MCS where it's not all the warm season kind of traditional what you think of as an MCS. It's more of like it's like an objective tracker version of an MCS, which is a little bit different. But we ran 1 year of CONUS404 through a radiative transfer model just to see if that would make it closer to observations, and it did. So we couldn't run it through the whole 40 years because it's just really expensive, but we did do it for a year, and CONUS404 then matches the number really well. Again, a lot more details I could talk about, but we have a paper under review, so hopefully that'll come out soon and you can read more details, or I'm happy to talk about it. So just conclusions for this part. Again, unified objective tracking over the whole of CONUS is very difficult due to the complex topography in the West. So this is, I think, the first study, to my knowledge, that applies a really comprehensive kind of synoptic to mesoscale storm tracking to a convection permitting regional model. A lot of this objective storm tracking is either focused on global data sets or climate models, or like really, really small scale, like tracking in radar refractivity and kind of little clouds. So this kind of bridges the gap a little bit and applies these to convection permitting models. Again, the low pressure system, as expected, spatial and seasonal occurrences compare well between CONUS404 and ERA5. And then generally the MCS spatial and seasonal occurrences also compare pretty well. There's kind of niche specific differences that we discussed in the paper. But the ultimate difference, the major one, was the numbers due to the difference in the brightness temperatures. So this is my PhD student, Kian. He has led most of the work on this. We have a paper under review. And our kind of next steps, what we want to do is connect precipitation to these different storm types, and also explore differences in the convective structures kind of between the different LPSs and MCSs. And then Kian is also thinking about, for the last part of his PhD, trying to develop a new kind of flexible water vapor tracking algorithm that he'll be able to link to this objective storm tracking to be able to constrain moisture sources of extreme precipitation events in reanalysis and also model output. So I know some people have done a lot of work with water vapor tracking, so I'd love to discuss that. But I think it's a really cool idea if we can pull it off. Okay, and now a couple of things about SNOWSCAPE. So as Nick mentioned, I honestly think I spelled the name wrong in my abstract because I always mix up like where these words are. But it's a study collaboration led by NCAR. We are involved at the University of Utah, some Utah State people. Rainmaker is contracted by the state of Utah to do the cloud seeding efforts, and then the state of Utah, some people are involved as well. And it's funded by the state of Utah Division of Water Resources. So it's planned for now as a 3-year project with a field campaign that happened in January to March of 2026. And so there's a lot of motivations, I think, for cloud seeding generally and studies on mountain snow. But specifically, we have a big problem in Utah, which is the shrinking of the Great Salt Lake. That is obviously not good for the ecosystems there, but also when the ground gets exposed, there's like toxic dust coming off of the playa where it's receding, which is not great. There's also increasing population in the Salt Lake Valley over the past couple years, decades, which is putting strain on water resources. We also have the Olympics coming back in 2034. So we do want to make sure there's snow for the Olympics, hopefully, Winter Olympics. And also we'll just, see a lot of tourism in Utah. So it's exciting. And obviously, as many of you know, the impacts of cloud seeding are extremely hard to quantify. So we're trying to do this study that involves not only atmospheric scientists, but also hydrologists to kind of study the whole life cycle of precipitation formation to water falling as snow and then going into the groundwater, running off into our reservoirs and lakes in Utah. So generally the goals of SNOWSCAPE, this was our study region here to the left. So this outline is the Great Salt Lake. Here is this view is approximately where the University of Utah is. And so we were kind of looking in this area near Ogden, Utah. The Snow Basin Ski Resort is also there, and we had some instrumentation there as well. And so we tried to set up this extensive observational network and also use WRF WeatherMod and WRF Hydro to study the seeded and unseeded storms, quantify the impact of cloud seeding on not only precipitation and snowpack, but also runoff, and advance knowledge about orographic precip processes and snowpack evolution in northern Utah. So we had a whole fleet of instrumentation. This isn't even all of it because this doesn't include the aerosol instrumentation we had, but we had quite a few instruments, including a microrain radar and precipitation gauges at Snow Basin, precipitation gauges kind of scattered throughout. The really important results maybe will come from these Dow radars. So we had a Dow on kind of the shore of the Great Salt Lake, and then one over on the other side of the mountain crest in Huntsville, Utah. And so my role in SNOWSCAPE, as Nick kind of mentioned, was I helped run the sounding, the radiosonde team, these were launched from near the radar in Syracuse, Utah, on the windward side of the mountains. And definitely this was my kind of first time really being involved in running and planning a field campaign. So there's a lot going into it. I definitely learned a lot. It was a lot of fun and really cool to have a lot of students involved. But one really scary thing was because this winter was a little strange, right? It was a little bit warm. And not a lot of storms came through, but we had a lot of convective events like in the winter. And so one thing that we really had to look out for when we were serving as chief scientists, which Nick did as well, was lightning for the scientists who were in the field. So that was something we had to constantly be on watching and tell them to go inside if there was lightning. And so here's just very early results. So this is looking at IOP total precipitation from our University of Utah gauges. So there's other gauges, including NCARs, that are not included here. And so broadly, the orangey boxes are the leeward side of the mountain crest, and then the windward side is the blue. And each of these is different IOPs. And say, just again, preliminary look, these still need to be quality controlled, but we kind of had a good variety, at least, of precipitation variation, where we had a couple of events where maybe there was a little bit more windward side precipitation versus the leeward side. And we also had, looking at the kind of range of IOPs, we had a couple cold front passages, some kind of weakly forced orographic events, and then some that were moist southwest flow. And so here is, let's see if I can get this to play, is some data from the windward side radar. And this shows during IOP7, this really strong cold frontal passage. So you can see it in the reflectivity. And then it comes up you can see the convergence zone really well in the radial velocity values. So it's just something a student sent me. I was really excited about some of the cool data. And because we have dows on either side of the mountain, we can really see the evolution of the front as it crosses over the crest. And so my master student, Zach, who's working on this, has started to kind of dig more into this radar data. Again, still needs some quality control. The ground clutter is still in there. But we not only did a lot of PPI scans, but we did some RHI transects. So this one goes from basically the radars like looking at each other, and then an upstream from this windward side radar, an upstream scan. And so you can kind of see, this is showing the occurrences of DBZ greater than 20 for different IOPs. And so again, it's still very preliminary, but just thinking about some statistics we can look at to try to understand the kind of variability in precipitation and snow processes that were happening during these different IOPs. So I'll just say thank you to Zach Atkins-Weltman. He's my master student that I'm co-advising with Jim Steenberg to work on this. And thank you to the rest of the SNOWSCAPE team, because it took a lot of people to put this whole project together and run everything. So for his master's thesis, Zach is kind of thinking about trying to understand how the upstream environmental conditions influence the evolution of clouds and convection, moving over this very narrow, steep mountain barrier in the northern mountains of Utah. Okay, I will say here, so here's my last slide. So being at NCAR, I just wanted to highlight a little bit of what I'm interested in. It kind of varies, but I think generally a lot of precipitation processes stuff in extreme storms, thinking about, again, precipitation efficiency has been really interesting to me lately. Anything tropical cyclones, as you can see. Again, moving to Utah, I feel like studying Western US mountain snow and kind of its predictability is definitely increasing in interest. And then, flash flooding and kind of the monsoonal convection in southern Utah and the southwest US has also been something I've been interested in looking at. And so put this picture here. I just want to put it because this was a picture from when I was here for the undergraduate leadership workshop in 2016. So it's, 10 years ago now. So that's me sitting in the C-130. Just wanted to put that up there to say, NCAR really makes an impact on people. And I'm sure I met some of you that are in this room during my visit there, and here I am now. So just thank you to all for working here and working with students, because it makes a difference. So, all right, thank you. I'll take any questions.
Okay, thank you, Alyssa. Before we get into questions, wait, hold on. 2 small announcements. There will be tomorrow, starting around 4:30 to 5, happy hour at Rayback Collective. If you're around, would like to come by, it'd be great. And then she also has a few more one-on-one sessions on Friday that you could sign up for. If after listening to what she has here, if you're interested, there's still some time slots available. So with that, let's start with questions. Rachel.
That was really great. I've known of your research from Hyperfacets and Kevin Reed for a long time, so it was great to see a full story of kind of what you've done. And also, I would like my source student to meet with you on Friday, so I'm going to coordinate that. They typically are booked too, but he said he could do it. So I have a question about your tracker and just Are you, just sorry, because I do this kind of stuff a little bit, but not on CONUS404. Are you applying a filter a lot of the times on this data? Or are you tracking on the raw field typically?
Yeah. So for the tracking, I'm pretty sure it's usually on the raw field, like the model, model falling terrain. But for the calculating the size of the impact area of the storms, that we applied a filter to the vorticity field because it's so noisy. I think that's it. We don't do like extensive filtering, I don't think before. Yeah, when I've tracked with, at least for ETCs on higher resolution data, I've had to apply like a Gaussian filter or something to not just get really noisy responses. Then also, other thing for your MCS tracker, have you compared this at all to like Jay Fang's like MCS tracker? Does it compare in some ways to that? I know he's more on, direct observations, but I'm just curious if that was that's an interesting question. We haven't dug too deep into comparing it with other MCS trackers, but it's probably a good maybe avenue to go around. I mean, we used Tempest Extremes for the tracking, which I think was part of like MCS MIP or whatever, where they did they too? They did. So you did MCSs with with Tempest Extremes, and we used settings that were for the tracker that were fairly similar to ones that were used before. So I imagine our results would probably be pretty similar. Just because we
And I don't know, does anyone know if MOAP, that's Andreas Prines, was that ever applied to CONUS404, or has that only been to global data?
I think Julia, when she did the precipitation efficiency work, I think some of the tracking she did was using MOAP. I think she, how I got involved was she found it wasn't really ideal for tropical cyclones in this case. And so since I already had the tropical cyclone data, I kind of provided that to her. But I think for everything else, she may have used MOAP.
Okay.
Yeah.
Cool. But really interesting. It was fun to see.
Yeah.
We're gonna
we'll go to one of the questions that's online on Slido. Which are more exciting, TCs or winter orographic snowstorms?
Ooh.
And have any TCs transitioned into a Utah winter storm?
Not that I know of. Not that I know of. That would be cool though. That would really combine all what I'm doing. That would be maybe in the future. Maybe we'll have tropical cyclones in December that turn into maybe that drop a lot of snow actually. I don't know. They both excite me. I'd like tropical cyclones just because I did all my work on, but living in Utah, and now I ski. When I moved to Colorado, I learned to ski. So that now I really care about the winter storms. It's hard to choose.
Any more in the room?
This was really cool work, Alyssa. It was
Thanks.
Nice to see everything you've done. I'm curious, when you looked at tropical cyclones, did you look at all like the location and how that maybe relates to precipitation or intensity? I'm just thinking if they had maybe started extratropical transition, but maybe weren't fully classified as that, or hit like orographic interaction, things like those.
Yeah, as far as like the differences between like the model and the observations, or
I mean that, but also like the precipitation changes, because I can imagine you had tropical cyclones in all different locations.
Yeah, no, I haven't really looked into that. The most I did was I just split it into when they were over the ocean only and when they were over the land only. So I didn't show any of that, but it'll be in the paper. And basically, when I remember, based on what I looked at, it was kind of as expected, where like when they're only over the ocean, obviously the intensities are larger, and the changes between historical and future are also larger.
Yeah,
when they're over the ocean versus when they move over land, those changes tend to be like subdued a little bit.
Okay,
if that makes sense.
Yeah, that's cool.
Yeah, but I haven't looked at anything like really done any like case study analysis or anything. I was thinking about doing that maybe, but.
Yeah, I mean, it's a lot of work, and you've done a lot of work already, so that makes sense. Thanks.
Maybe a good project for undergrad or something.
Yeah. Hop back onto Slido, where two-parter. How does the tracking isolate the TCs from other storm types?
Yeah, that's a really good question. So this use it to separate like the different types of low pressure systems. So extratropical, tropical, dry or whatever. So that's all comes from, we kind of adapted this Cyclops tracking framework, which is kind of its own tracking framework based on Tempest Extremes. But that I don't remember the details, but it's all based on different like measures of, is it a cold core or is it a warm core storm, depth of moisture, stuff like that. So it's all based on physical variables. It doesn't do it based on any like latitude limits or anything kind of subjective like that. But yeah, that was led by Yushan Han and Paul Rick at UC Davis. They kind of created that tracker.
That maybe sort of gets into the second part of the question. Is the tracking good for small storm systems?
I mean, it definitely tracks a variety of different things, like even like small kind of like tropical depressions that aren't tropical cyclones. I guess it depends what you think. Small, I guess, yeah, I would have to think about like what, or maybe ask what exactly, like individual convection, maybe not, it doesn't get that, but like weak, small, low pressure systems, I think it does okay, yeah.
Thank you. Great talk. So I have a question about your PGW simulations. So you mentioned that you used SSB3 to SSB7, but all of your results are only future. So does the results are similar for different SSBs?
I don't think so I use these are the CONUS404 simulations, which were run at NCAR. And so I didn't run them. I don't think they did at different SSP scenarios. Someone can correct me if I'm wrong. I think they only did one just because they're so expensive, because they're so high resolution over the whole US. Yeah, people are nodding, so I think that's correct. Okay. But it'd be nice if they did have different ones, but yeah, understand it's super expensive.
Oh, another one. Okay.
Hi, Alyssa. Here. This is CC Chen, and great talk. I'm curious about the SNOWSCAPE campaign, and you mentioned that the storm seems like abnormal this year, and you see a lot of convective storms instead of like more typical winter storm.
Yeah.
So have you looked into the storm characteristics or like storm statistics? Are there more extreme precipitation out of those convective storms, or?
Yeah. That's a good question. We haven't, I kind of said that, but I haven't statistically or looked at it, quantified it. But yeah, it would be kind of interesting to do kind of a comparison of other years. We just wouldn't be able to use the observations that we have, right? Because it was just a one season field campaign, but could see, yeah, maybe people doing some work using, maybe we could characterize it based on the National Weather Service Salt Lake City radar and kind of see how abnormal the year was. I know they're kind of doing that on the hydrology side to see how this year kind of compared to other runoff years. But maybe we should do something like that on the atmosphere side just to see how abnormal it was.
Yeah. Thank you.
Yeah.
Any more questions? I don't see any on Slido in the room. No? All right. Well, thanks again, everyone, for coming. And thanks again for Alyssa as well for this seminar.
Yeah. Thank you all.